So what we want to do is to build on what we did yesterday, where we were estimating the slopes of tangent lines from data. We're now going to try to incorporate the concavity, which is actually going to allow us to find an error estimate for our estimate. Meanwhile, what's the task? The task is, here's a bunch of data, and we're being asked to find the slope of the tangent line at point 8. Now I'm going to do a little bit of what I did yesterday. I'm just going to connect them up with these little lines so I can actually discuss what's going on. What we did yesterday is we looked at this slope right here and we said it looks too small, and we said looked at this one and said this slope is too big, and then we found the average of the two. Now the thing is, this graph is concave up. Now what does concave up mean? It means the rates of change are increasing from left to right. What does that tell us here? That tells us that this slope here not only looks smaller than the slope of the tangent line here, it's guaranteed to be smaller than the slope of the tangent line. So the slope here is going to guarantee to be too small. The one over here, not only does it look steeper than the actual tangent line, but because this is concave up, it's guaranteed to be too big. So the slope here is guaranteed to be too small. The slope here is guaranteed to be too big. Now we're going to try to use that. So what I'm going to do first is just draw the line that goes through the first 2 points. And I can see that that's actually going to be too small. That's going to be smaller than the slope of the tangent line. Over here you can actually see me doing the calculation, and you can see that the slope of the red line, the one that's too small, is 0.39. Now I'm going to go and put in the line between the second 2 points. That one, the slope is guaranteed to be too big. It's guaranteed to be too big because this is concave up. So what I have is I have a number that's guaranteed to be too small, 0.39, and a number that's guaranteed to be too big, 1.243333333. Now, like we did yesterday, what we want to do is find the average of the two as our best guess. Now, our best guess is just going to be 1.24 with lots of 3's. That's as far as we got yesterday, but we're actually now going to use the too big number and the too small number. What I want to be able to do is find the average. The average is 0.816666, which is the slope of the line between this point and this point. But we know that 1.24 is too big and 0.39 is too small. If 0.18666666666 is too big and 0.39 is guaranteed to be too small, then the furthest away our best guess here can be is going to be the difference between our best guess and a number that's guaranteed to be too small. So here I'm going to take my best guess and subtract a number that's far enough away that I know I've gone past the actual answer. So the distance between our best guess and our lower bound is at most 0.42666666. What does this tell us? This says our answer has to be within 0.42666666. So what we get is something that's better than yesterday. We get a best guess of 0.81666666 plus or minus 0.42666666. Now, two things about that. Number one, we get a pretty good answer. And number two, we got a terrible answer. Look how big our error is. Yes. This is the problem with error estimates. It's like if someone said find a better guess, we can't find one because we can't just add data. So that leads us into all sorts of problems later on.